Hello. So we're on our last Unit 4 presentation. As always, dog. She's sleeping though. Oh, he's so cute. Oh. Okay. So today we are talking about entropy and Gibbs free energy. In reference to like collegiate level, this is a lot of Gen Chem 1 and then a little bit of Gen Chem 2. I talked about this stuff for probably, most of those two classes. So this is a big part of that collegiate chemistry level. So today is entropy and Gibbs free energy, but at first we're talking about thermodynamically favored processes, TFP, which they put into a little abbreviation. Thermodynamically favored process just means that it works at like normal conditions. So like, for instance, iron rusting, it will happen eventually. Or salt dissolving in water, it will happen eventually. Or water evaporating at 25 degrees Celsius. These are processes that we don't have to push in any way. They happen without our assistance. So non-thermodynamically favored process just means that it needs assistance for the reaction to occur. So water is not going to boil at 75 degrees Celsius at 1 atm. We're going to either have to change the temperature or change the pressure. Water is not going to freeze at 15 degrees Celsius. You got to change the pressure or temperature. And then iron oxide is not going to turn back into regular iron, is what that last equation is saying. A process that is thermodynamically favored in one direction is not thermodynamically favored in the other direction. So if it goes one way, it takes effort to get it to go back to the other way. So it says here water turning into a solid at negative 10 degrees Celsius is thermodynamically favored. It's going to turn into ice. But a solid turning to liquid at negative 10 degrees Celsius is not thermodynamically favored, and you're going to have to you're going to have to change something in order for it to turn into the liquid again. Exothermic reactions are often thermodynamically favored. Generally, nature favors a process that causes a reduction in energy. Nature is happy to just kind of dispel energy. In an exothermic reaction, the bonds in the product contain less energy than the bonds in the reactants. So there's less energy in the products than the reactants, and so it is thermodynamically favored in that way because nature is like it doesn't really want all that energy, and that excess energy is released as heat into these surroundings. Endothermic reactions can be thermodynamically favored. Evaporation is thermodynamically favored. That has a positive delta H value and is an endothermic reaction, as well as C3H8 liquid turning into a gas, also evaporation. It is thermodynamically favored. Dissolving soluble compounds is thermodynamically favored, so having those compounds turn into their ions, even though it's splitting into more stuff, its delta H value is positive as it being an endothermic reaction, so the heat is actually coming into the system, but it can be thermodynamically favored in some instances. Entropy. Entropy is like, it's like talking about space. It is just entirely awful to talk about. Because it's literally about disorder. Entropy is the disorder of a system. Is it messy or is it not? That's entropy. If there is more disorder, then entropy is bigger. If there is less disorder, then entropy is smaller. We want more disorder, apparently, in the universe. A positive value for delta S is favorable, so we do want our products to be more scattered than our reactants, which is interesting. So think of like tennis balls. Okay, dog. Okay, all right, thank you. You're a good boy. Okay. Delta S, the entropy of the products minus the entropy of the reactants. Think of a tennis ball pyramid. If the pyramid is like perfectly aligned and it's straight and it's pretty, that is less entropy. If we throw all the tennis balls on the floor, greater entropy because there is more disorder. Great to talk about. Increases in entropy are favored, so if your house gets dirty, apparently that's favored. Making a stir fry as opposed to just having these separate ingredients. The impossibility of maintaining a perfect lawn is favored. Spilling a glass of milk all over the table or breaking a window, those are all increases in entropy and they are favored in these reactions. Laws of thermodynamics. First law of thermodynamics says that the energy contained within the universe is constant. So, energy is constant. We cannot create or destroy it. It is, you'll see. Second law of thermodynamics says that the entropy of the universe is constantly increasing, which kind of means that the universe is increasing, but I'm not going to go into that. Okay. So delta S is equal to the entropy of the products minus the entropy of the reactants. Same equation as we've seen every single time. This equation is in your reference table, so you cannot mess it up. So it's the degree of disorder contained within the reactants is a constant. The degree of disorder contained within the products is a constant. So we're not caring about how we get from one place to the other. The route is not important. We just care about the products and the reactants. Delta S will be greater than 0 for these processes. Melting, so going from solid to a liquid, obviously our disorder is greater, so our delta S will be greater than 0. Vaporization, same reason. My dog is chewing on a toy. Yes, you. So sorry for the weird chewing noise. Reactions where the products are in the same phase as the reactants but contain more particles than the reactants. So something that splits up into ions or a single compound in a reactants turning into a bunch of different compounds in the products. Reactions that produce more random phases are going to be an increase in entropy. Making most solutions usually gives us a delta S of greater than 0, and adding heat normally gives us that as well. So delta S is greater than 0 when melting. So obviously, over here, we've got a really good order, a bunch of these little Mickey Mouses, or H2Os. I think my middle school teacher called them Mickey Mouses. So we have a small s because this is pretty organized. Over here, we turn into a liquid. It's less organized, it's a larger S, but it's not that big. But when we go into the gas phase, we have a much higher entropy value than when we did in the liquid or the solid phase. Delta S is greater than 0 when products have more particles. So in this example, we start with this one reactant and we turn into all these products. Increasing the number of moles increases the number of potential arrangements, and changing from liquid to gas increases the number of potential arrangements. So, in all those cases, delta S will be greater than 0. Delta S is usually greater than 0 when making solutions with solids or liquids. An ionic compound is generally very organized, so this is your NaCl right here. But as soon as we put that into solution, it just kind of dissolves everywhere and blah, 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 and those ions are just disordered everywhere. They're much more disordered than they were before. Delta S is less than 0 when making solutions with liquids and gases. So when dissolving a gas into a liquid, your entropy will decrease because up here, your gas is just free reign. It's just running wherever it wants to. But as soon as you put that into a solution, it's kind of contained within this box, and you're losing the rapid, chaotic movements that you would have with a gas particle. Delta S is greater than 0 when adding heat. So obviously, if we add heat, then our entropy will get bigger because we go from a solid to a liquid to a gas. So if we add heat, our delta S is going to increase. Also, when adding heat, the distribution of the kinetic energy increases. So when our kinetic energy increases going this way, our gas particles are getting much quicker, and more gas particles are getting quicker. So back here, our kinetic energy was lower because our temperature was lower, and only this, there are a lot of particles, but they're not going that quickly. They're just they're walking. But put a bunch of middle schoolers in there, they're jogging. I mean, they're kind of quick, but then put like all-star soccer players up there, probably pretty chaotic. I mean, they have a place to go, but still. Delta S is going to increase when the volume increases. So if I have two gases, these are two different gases. This is a smaller box. We're kind of contained within the smaller box, but over here we can kind of space out and we have more disorder. It's like the difference between putting people in like a Dollar Tree versus like a Walmart. Much more disorder in that Walmart because they have more places to go. Calculating delta S is the same as we have always been doing it. So delta S, and this is that standard entropy of the reaction, equals the sum of the entropy of the products minus the sum of the entropy of the reactants, and make sure that you're using these stoichiometric coefficients in front of those when doing the standard entropy values. So in this example, calculate delta S for the following reaction at 298 K. So it's going to be, it doesn't give you values, but you can write it in the form. So delta S is equal to, we don't have a coefficient in front of here, so it's just going to be N2O4 value minus the sum of, no coefficient here, so it's just N2 plus 2 times O2's value. And that's how you'll get your entropy, or your change in entropy. Oopsie. Okay. How can you tell if a process is spontaneous? Spontaneous meaning thermodynamically favored. Exothermic reactions are favorable. So if it's exothermic, your delta H is less than 0. Systems that create disorder are favorable, so our delta S is greater than 0. So if we have an entropy that's positive and an enthalpy that's negative, that is going to be the most favorable. So two methods for determining if a process is spontaneous. First off, we can talk about delta S of the universe. So the universe, we just kind of say, is the surroundings in the system. We just say that is the universe because the surroundings can honestly be like everything around it, around the system. So delta S of the universe is equal to delta S of the system plus delta S of the surroundings. If delta S of the universe is greater than 0, the reaction is thermodynamically favored. So if the change in the system plus the change in the surroundings is greater than 0, then it's going to happen. Delta S of the surroundings and delta H, heat flow links the system to the surroundings. So in an exothermic reaction, the heat is leaving the system and going into the surroundings. Delta S of the surroundings is going to increase. So our delta S of the surroundings is going to be greater than 0. In our endothermic reaction, the heat is going into the system. So the entropy of the surroundings, the disorder of the surroundings is going to decrease because we don't have that heat favor for us. And so it's going to be less than 0. So exothermic reactions are going to be much more favorable. If a process increases the entropy of the system, so the system is positive and is exothermic, so the delta S of the surroundings is positive, it must also be thermodynamically favored because the delta S of the universe will be greater than 0. We can also look at Gibbs free energy, and that's going to be your delta G. So G is Gibbs free energy. That's all it is. And it is actually just the delta H minus the temperature times your delta S. And this reaction is in your reference table, so you cannot forget it. It is one of the most important reactions in this thermodynamic stuff. So if delta G is less than 0, the reaction is thermodynamically favored. We want delta G to be negative. And it is in kilojoules. But honestly, if you see it in joules, I mean, you know how to convert that. So delta G equals delta H minus T delta S. There are two ways to calculate it. Number one, we can calculate delta H using calorimetry, Hess's law, or enthalpies of formation values like we have been. Calculate delta S using the entropy values they'll give you, and then just use that equation to figure out delta G. Again, I don't have a calculator in front of me, but I can kind of just like write stuff out. Example number 1, find delta G for a reaction if delta H equals that, delta S equals that at 32 degrees Celsius if the reaction is thermodynamically favored. So, delta G equals negative 218 minus T, which you need to convert to Kelvin. So, let me see here. Do you? Yes, you do. So, it's going to be that negative 218 minus 32 plus 273 times negative 765. And that'll give you a delta G value. And then it's asking, is the reaction thermodynamically favored? If delta G is positive, then no. If delta G is negative, then yes. And you can easily calculate that on your phone. Example number 2, at what temperature does the previous reaction become thermodynamically favored? Assume that delta H and delta S do not change as temperature changes. So apparently, this first one was not thermodynamically favored, meaning delta G was positive. So, I can figure out when it'll turn thermodynamically favored by doing pretty much, I can just say negative 1 equals my delta H value, which we do know, minus T, which is your X, that's what you're looking for, and then the delta S value that you had. And you can easily calculate that. You could even use 0 or negative 0.1, whatever you want to use, it'll get you in the ballpark. Temperature and spontaneity, whatever. Delta G equals delta H minus T delta S. So if delta H is negative, but delta S is positive, you will be spontaneous at all temperatures. If delta H is positive and delta S is negative, non-spontaneous at all temperatures. Because basically this negative, it'll be minus a negative value right here, and which is plus, and then your delta G will like automatically be a positive value. If delta H is negative and delta S is negative, it'll be spontaneous at low temperatures, non-spontaneous at high temperatures, and the opposite for both positive. This chart you don't need to memorize. I mean, it's good to know, but you can calculate these things pretty easily by just using some fake numbers that you come up with, and it's not that difficult. So, example, if delta H equals negative 163 kilojoules and delta S equals positive 148 joules per Kelvin for the following reaction, is the process thermodynamically favored? So you can either do the reaction, or we can just kind of look right here. So if delta H is negative and delta S is positive, then it'll be spontaneous at all temperatures. And that's pretty much all you need to say. The other way of calculating delta H is using the delta H standard of formation. So delta, whatever, is the free energy change that occurs when 1 mole of the compound is made from its elements in their standard states. So it's the same exact thing as before with the 1 mole thing. For an element in its standard state, that delta H value is 0. I feel like I'm yelling. Oh well. So for this reaction, it's wanting you to calculate that delta H standard reaction. So, delta G. So I do my products minus my reactants. So I'm going to do delta G standard of reaction equals the products minus the reactants. That's 0. And that's 0 because they're in their standard form. So I'll just do the value for Al2O3. And that's multiplied by 1 because I don't have any coefficient. Minus, multiplied by 1, Fe2O3 value. That's super ugly, but whatever. You get the point. And they'll give you those values. Thermodynamically favored processes are not necessarily fast. For example, iron doesn't rust within seconds. It takes a while. The rate of the reaction is determined by chemical kinetics, not the thermodynamics. So many of them do not occur at a measurable rate. They just kind of take as long as they're going to. Using external energy when delta G is greater than 0. External energy can drive reactions, so if our delta G is positive, we can use electricity or photons or changing anything in order to get that process to go forward. So this is just an example. So initial step in metabolic breakdown of glucose has a delta G that's a positive number. The conversion of ATP to ADP is a negative delta G value. So what they do is they put those two together, coupling a non-thermodynamically favored process with the conversion of ATP and ADP makes the overall process thermodynamically favored because adding these two numbers up gives you a negative value, which is thermodynamically favored. And that is it. So that is entropy and Gibbs free energy in a really, really quick version. But the reactions or the math is pretty simple to follow. So don't worry about it. Just let me know if you have any questions.